The 3D structure of DNA does not depend on its primary sequence. What is its primary sequence? What does that mean? And then it says not the case for proteins. So what does that mean? First of all, what is primary sequence? Yes. Order of the bases. Love it. It's A, T, G, C, T, G, whatever it is. And we said this, we talked about this before. Primary sequence for proteins is just name me the amino acids in order. So it's proline, glycine, lysine, thymine. I don't know them. I'm so bad, right? I use the same ones over and over, the ones I like know the best, right? Tryptophan, there's a good one. All right, so primary sequence, just the order of the bases. It does not matter what the order of bases look like. DNA will always make this structure. It does matter what order the amino acids are in a protein. It dictates what it folds into and what types of structures it makes. Okay? Bases always pair in the same way. They always orient in the same way relative to the backbone, and they can stack neatly on top of each other. It's sort of the vertical helical axis direction. Okay? And that is especially stable. Cooperativity. Cooperativity, also a big chunk of chapter when we get into molecular recognition and we talk about cooperative binding when actually like proteins and drugs are binding. But cooperativity also occurs between two DNA strands, right? An individual H bond may be weak, but favorable. The formation of the helix is cooperative, becoming increasingly stable as more and more bonds are formed like a zipper. Okay? So basically, as the first one forms, these next two get in close proximity, so it's easier for the next H bond to form, and it sort of zippers up into the DNA strand. Mismatched DNA sequences would not have matching base pairs and thus would not be able to form a helix. What's happening instead? What's going on in between the zipper that once they get close to each other, it doesn't work? Thoughts? Yes. So van der Waals forces between bases that are parallel like this to each other in the vertical direction are actually awesome, hugely important, very stabilizing. Okay, so what's coming up next? This is when I have a mismatched base pair and I want to come together. What's in between these strands right now? Water. Water, right? So when I actually have my, bound together double helix, I'm making H bonds with my paired base. When I have a mismatched base, or I should say when they're unzippered yet, I'm not done creating my double helix, I have a whole bunch of water in here interacting with all of the hydrogen bond donors or acceptors. And so when I go to zipper this up, I have to kick the water off in order to make these H bonds. Okay? These H bonds are ever so slightly stronger energetically than a water H bond. But it takes energy for me to kick all of these off in order to make this more favorable bond. Okay? So if I think of sort of sign convention, the positive energy component for breaking all the H bonds between water and the bases on a single strand, and then subtract from that or combine from that, sum them up, but use my sign or subtract. All of the contribution from the formation of H bonds between the bases and the double strand, I get this net change in energy. I'm asking for a net change in energy. This is what I'm talking about. And in this case, it is net negative, so you expect it to happen, but it is a very, very, very small, sort of insignificant contribution, such that even one mismatch might destroy this. Okay. So instead, these van der Waals are the really stabilizing piece of DNA. And they appear here, right? So when all the bases are aligned nice and vertically on each other, in between them, with all these van der Waals interactions, okay? So in addition to hydrogen bonds between bases or base pairing, there's also these electrostatic interactions that come from the aromatic rings. The symmetry of the rings will lead to electron configurations that can have really favorable, there's a lot of different words for this. Ring stacking, pi stacking, base stacking. I might use any of them. You might read any of them somewhere. They're gonna mean essentially the same thing. Okay. Here's a couple other of sort of illustrations of what that looks like, right? So we have inter-strand H bonds intra-strand pi stacking, right? So these are the same strand. I won't ask you anything about an H-bridged chelate ring, so don't worry about that. I pulled this figure from another source. Good paper, go check it out, but you don't have to worry about this little pink part here. So again, this is showing you the distance between adjacent, sort of in the vertical direction, these stacked bases. 3.4 angstroms, does that seem like a reasonable distance for van der Waals to happen over? Sounds good, right? Let's go. So, van der Waals, we said they're additive, right? We talked about gecko feet, right? So if you add a bunch of them up, they become very strong. How many van der Waals interactions do you think can happen between any two given rings in the vertical direction? Just a guess, maybe? I guess any number. I mean, you can maybe think about the atoms in the two, like in a double ring, and maybe there's a cap on how many could be there, but thoughts, guesses? $15. Who's already read all these notes? 15 is the right answer. It's in the note section of this. Up to is about as many as 15 simultaneous on any given one pair of bases, right? So that's why when these add up, very stabilizing. Bases are going to be flat. They are perpendicular to the helical axis, and they pack very nicely and neatly. Like we said, symmetry in the rings leads to these van der Waals. We'll call it ring, base, or pi stacking. Base stacking is the significant interaction driving the formation of this double helical structure. Okay? A single helix charges, the negatives trying to get away from each other. But in the double helix, what makes it very stable, less about shape, more about stability, is the van der Waals. So I kind of have this slide. This is, I can't remember what review section I pulled this from, but I kept saying, like, what's the driving force for this? The driving force, first of all, use of force was a really bad choice of word on my part, and then also what sort of dictates shape and stability isn't always the same thing, right? And so in this case, shape is a little bit more about those negative charges. Stability is really provided by van der Waals.